It is high case, low case, and the base case. It says, okay, it defines the yellow line as the low case. Why?
If the structure is a little bit
The lowest it would possibly be.
Deeper. The structure, when the structure is deeper, so which parameter, which data we get less value? That's why it's the low case. Huh?
I think hydrocarbons, lesser hydrocarbons.
Yes,
Or
volumetrics, because our gross rock based on this yellow line, yellow structure is going to be less than the base case red and the blue. And blue is going to give us the highest volumetrics. That's why it is high case.
Mm.
And then we calculate this, okay, volumetrics from the structure, which reference point, which depth?
seismics.
When is the reference point above that value, we calculate the volumetrics.
I think it was taken from the seismics or what?
Nope. Okay, we calculate the volumetrics between the top structure and
Base. Oh, contact, fluid contact.
fluid contact. So above the oil water contact, we calculate the volumetrics, okay?
Yes.
And think about a person, smart person, get the structure, and then he puts the volumetric here, okay, sorry, contact, oil water contact here, and calculate the volume between top structure and that level. So what is his mistake?
He considered all thick formation from, I mean, from the base to the maybe this is the only layer where hydrocarbons are there.
Exactly. If we have the contact here, we should calculate the volume between the top structure and the contact minus base structure and the contact. Okay, all this volume, this area has to be subtracted, right?
Yeah.
If he calculates the volume between top structure and the contact, he would add all this area too.
Yeah.
So yeah, you see, you know, in calculation, what kind of mistake can happen?
Yeah.
So this one is showing the uncertainty, top structure, base structure, and free water level. Here, the top structure uncertainty, like you see here, okay, between blue and yellow, doesn't affect too much. Why? Because our free water level or oil water contact is so deep, if the structure goes a little bit down, a little bit up, doesn't okay change. Our reservoir thickness is thin and above the contact much higher, and this change does not affect too much. That's why you see there are cases, and each reservoir is unique. That's why, okay, there are cases, for instance, top structure wouldn't be such important, so you shouldn't spend money on seismic, and you shouldn't spend so much on the seismic, because top structure goes a little bit down, a little bit up, still above the free water level. But that's why you have to analyze each parameter, what is the effect on your results, okay? And then define the important parameters and go for it. So what does this graph shows, Tiffany?
Core porosity versus log porosity. So with all of the different ones, upscaled well logs, and I don't know what the first one is, but just varying from, I don't know what the both sides are though.
You see the mean value, okay? in scaled up core porosity is 18.8, which is somewhere here, the mean value. But when you look at the log porosity, it's 17.8, somewhere here. So there is a difference, okay? And almost how many percent?
One.
1.7%, almost, almost 2% difference between core and the log. And you see the core is showing higher or lower?
Or is showing higher. Or for mean higher, isn't it?
Yes, the mean is showing higher. Yes, because there are more points in above the mean value. You see, because our graph is on the right side, and then the list value is like 3%, 8%, 9% is not as much as here in the log. Log shows more in the lower area, right? So where does this error comes? Okay, Gazanfer, why do you think that the source of error here?
Actually, there are a couple of things here. Like, first of all, we have to see that what type of porosity log was run, right? If it is a neutron porosity, it has, a lot of environmental parameters we have to use in that to negate the effect of gamma ray as well, because if it is neutron porosity tool, it reads gamma ray. And if it is a CTN type of tool, it reads neutron, then we have to use it thermalized neutron. Again, temperature and pressure effects change the readings a little bit. So we have to apply mud corrections, borehole, geometry, like for example, caliper logs. So all the corrections have to be applied on logs. And if it was the, in the neutron porosity, one more thing, like if we are using neutron porosity tool, we have to use this, and we are using it in sand. We have to apply correction as well, because generally it is calibrated on limestone. So this is one of the another important thing, that where exactly in which formation we are using this tool. And if we are using borehole or sonic, and borehole sonic porosity, then again there are some type, we have a lot of noises as well in sonics. And if we are using density porosity, then it could be a good one. And I think it's more reliable, density porosity.
Okay, perfect. All the things that you're talking about is correction on the log curves and which log curve you are going to use for calculation of the porosity, so on and so forth. Because you are taking core porosity is your hard data. It is direct measurement to the rock, but the log porosity is calculation plus the measurement of the tool. And you are trying to fix those things, okay, on those tool error and calculation error and so forth, okay? So the first thing what you have to do before you do modeling on the porosity, okay, you have to correct your log porosity by comparing to the core porosity, okay? So that's a good result. So a correction on your log curves based on the core data. That's the conclusion. Exactly.
Simple.
So you see, if you remember last time, we have calculated 7 or 6 cases, 6 realizations, okay? Realization number 1, 2, 3, and then which parameter we use to calculate different realizations, Tiffany? Which parameter we have changed to calculate?
I'm not sure for this.
Seed number, seed number.
Oh, the seed number. Okay.
Yes, stochastic modeling, which was the Gaussian simulation. Okay, SGS, sequential Gaussian simulation, and we changed the seed number to calculate different realizations. And you see, in each realization, the minimum, maximum, and mean value of the porosity is changing, okay? You see here is 14.54, 14.6, 63, 14.33, and then if you look at the highest is 14.99, and the mean value among this 14.33, and the difference is 0.66, almost 0.5 0.5% is the difference in the realization, okay? Because of our processing techniques, we are getting more than 0.5% porosity is different. And they are all equiprobable cases. Okay, at the end of, if we drill thousands of wells, okay, and then look at the results, it can be realization number 1, 2, 3, 4. They are all equally probable cases. That's why we might have to consider this or this or this or this. And the difference between them is 0.66. So that's the uncertainty based on our processing techniques. So this one is uncertainty based on what? Between 18.8 to the 17.8. This is the uncertainty based on what?
Based on core.
Based on measurement techniques. If we measure it, if we measure the porosity on core or log, that's the difference. And this one, 0.66, is based on the processing techniques. We are using the stochastic modeling processing, and it might be uncertain at this level. So you see, measurement is making difference, processing is making difference, so we have to consider each one of them. That's how we are considering, okay? So porosity measurement, phi E, effective porosity, C-pore, core porosity, and porosity statistics you are looking and comparing, okay, at each subzones, okay, because each subzone is showing different characteristics of the rock. That's why you are comparing at that subzone separately. And you see here, the difference is 2.05 porosity unit, PU. And then this 2.05, when you are modeling, you have to, at mean value of your model, you have to calculate minus plus, okay? So this is your uncertainty, you calculate, and you end up with this 2.05. That's why in your model, you have to push 3 cases. Okay, your base case is showing at this mean value, and minus 2.05 is your low cases, and plus 2.05 is your high cases. You have to shift entire your model. If you use this value, add it to your base case and use it in your simulation, or subtract 2.05 and then calculate your porosity model and use it in the simulation. So this is a technique of uncertainty modeling, okay? You are considering your uncertainty in the simulation phase. So is this a deterministic way of calculating uncertainty or stochastic way?
Mix of both.
You think both?
I think so.
Tiffany?
I was going to say stochastic, but
Okay, both you are wrong. It is,
Oh.
it is deterministic because you are fixing your error 2.05. You're subtracting, adding, and calculating your high base case and using this 3. Okay, it's a fixed amount. It is a constant amount you are playing. That's why it is deterministic. You are determining your uncertainty. If you use, where is this? Okay, you see there's 8, 9 realizations. Okay, the highest is 14.9. This one is your high case, and the lowest is 0.33. This one is your low case, and 0.62 is the base case, 52. If you use this one as a base case, is this stochastic or deterministic technique?
Deterministic.
It already tells you that stochastic.
yeah.
So by stochastic technique, you are calculating your cases and using it. So that's how stochastic versus deterministic is playing in the geostatistics. So you see, in this porosity model, uncertainty modeling, okay, you have different scenarios, okay, which is called scenario-based uncertainty. And each scenario, you are using different geostatistic technique and different data style, let's say, and different trend and correlation coefficient and variogram. So you end up with the 6 cases. And each case generates different porosity model, and you use it in your simulation. And then what parameter about the 6 cases is going to tell you which one is the low case, which one is the high case?
Remember?
Which one?
Seat
So we are
number?
gonna check the 6 case in simulation and calculate something as a result of porosity model and tell you that, okay, if you want to rank the 6 cases, this is giving you this, number 2 is giving you this, number 3 is giving you this, so you can sort it. You can tell this one is high case, this one is low case. What is the result?
4.
Porosity is directly affecting the volumetrics. Your STOIP, initial oil in place, is your result. Okay, so there is a calculation of your STOIP, original oil in place, in static model and in dynamic simulation. Okay, and there is a difference between, because in dynamic simulation, they are calculating the saturation, for instance, you know, according to their relative permeability curves, their PC, capillary pressure curves, and their height function, whatever. And in your static model, you might be considering all those things, or you were just calculating saturation based on your saturation log. So that also creates a difference between dynamic and the static volumetric. That's also a source of error. Which one do we have to consider? Which one is more realistic?
Dynamic.
Of course, dynamic, because they are more realistic on the saturation. Oil saturation, water saturation, they are more realistic, they are more in the dynamic side, and then they are considering much more data and so on and so forth. And then they are testing all these calculations against what? How do they test their saturation model and then verify the accuracy?
Saturation from the well test.
Exactly, from the well test. What would be the water cut? Yeah, that gives the verification of the saturation model.
Yeah.
You see, you know, you have to know at what level, what data is critical, how do you compare, and compare it with what, and verify. How do you verify it? All these steps has to be consciously decided. Otherwise, you are going blindly.
Okay.
I will tell you a case in next session. So let's
Okay.
stop it. Come back in 2 minutes. Okay.
Okay.
Okay.